Welcome to our third lesson on graphs of motion. Today we're going to be taking a look at a combined graph question. Now the question is going to start off by telling us that the motion of an object that was traveling east originally is represented by the following velocity time graph. Now it's important before you even take a look at the graph to note that it was traveling east originally and that it's a velocity time graph given. So here is our velocity time graph. We can note that there's some motions and points are indicated with letters A to F. Now the first question asks us to describe the motion of the object during the 9 seconds that's shown on the graph. Now when we're going to explain this motion, we're basically going to break it up in different increments where we see the same motion occurring. So from A to B, you'll see that there is basically a straight diagonal line upwards for the velocity. So we're going to indicate from 0 to 2 seconds is our first motion. Our second motion is B to C, and that's from 2 to 5 seconds, where it remained a flat horizontal line. From C to D, it's from the 5 to the 6th second, it's in this case another motion with a diagonal straight line downwards. From D to E now you'll note that we're going to the negative part of my graph, and that's between the 6th and the 8th second, where it's going to be, in this case, a straight diagonal line but downwards. And the last part of the motion is going from E to F, which is the 8th to the 9th second, and it's now going to be a diagonal line upwards but still in the negative part of the graph. Now let's start off from the 0 to the 2 seconds. We can see that we started at 10 meters per second and will be, because of this is a straight diagonal line upwards, traveling at a constant acceleration until 15 meters per second. So from 0 to 2 seconds, we start at 10 meters per second, as we said, have a constant positive acceleration. So this is then my motion that I'm describing till it reaches 15 meters per second. From our second to our 5th second, we'll notice that there is a flat horizontal line, and that means, as you can see, it stays at 15 meters per second and is thus indicated as a constant velocity. And it's important to indicate the specific values that you do have as it's given on the graph. And then when we take a look from C to D, we'll note though that from the 5th to the 6th second, there's this diagonal line, but it's now pointing downwards. And we went from 15 meters per second to 0. So that means we're going to have constant negative acceleration until it comes to a stop, because 0 meters per second means that it's come to a stop. Now let's quickly take a look at our specific directions for this 3 motions up till number D. Note that they are all positive velocities. That means that they're going in one direction, and this original direction was given as east. So as part of our explanation as what's happening in every motion, we need to indicate that it is still traveling east from 0 to 2, from 2 to 5, as well as when it's slowing down here from 5 to 6, it's also still traveling east. Now, when we get to our next part of the motion, we'll note that we've got now a negative velocity because it's in below our 0 axis. And negative means it goes in the opposite direction. Now, one important thing that you'll always need to take into consideration is when an object is traveling in the opposite direction of which it was originally traveling, and you need to determine the motion from a graph given, we use the mirror image. Now, mirror image just literally means like when you in grade R, you painted a piece of paper full of different colors, and then you folded that piece of paper in half, you squashed it, and then you opened it up. And you would note that the one half of the paper looked exactly the same as the other half. And this is what we refer to mirror image. So what we will be doing is we will be taking our piece of paper, as said, that means our graph here, and we'll fold it here on the time axis, so that this bottom part of my graph, which is now going in the opposite direction, will, when I have opened up again, form an image as such. So this is now mirror images, seeing that we folded the paper right here on the x-axis. Now it's easier for you to determine from this motion, taking a look at the graph shape, what was the actual motion. So we can see from D to E, it was going in the opposite direction, which is now to us west, but when it was doing that, it was actually accelerating, because a straight diagonal line upwards indicates to us acceleration. You can see that it started off at the 0, and then when it increased its velocity, it went up to 10 meters per second. So it accelerated, but now in the western direction. So between 6 and 8, it's still a constant positive acceleration, but it's now going in a western direction, and it started from north and ended up till 10 meters per second. And you'll only be able to see that it's constant positive acceleration if you do the mirror image of the part of the graph below the 0 axis. Now let's take a look at the last part from E to F. This is still falling underneath my 0 axis. That means we're going to still look at the mirror image on the other side, taking into consideration that it's traveling west. Now you'll see that it is going from a diagonal line from the top to the bottom, which indicates to us constant negative acceleration. And you can see that from your values, it went from 10 meters per second back to naught. So it came again to a stop, but now, remember, it's in the opposite part, so it's traveling west. So constant negative acceleration, but going from 10 meters per second to naught and traveling west. Now our next question asks us to determine the distance covered by the object during the 9 seconds. What's important to note here is that they refer to distance. Now there's a difference between distance and displacement. Distance was a scalar quantity, and that meant that it only had a magnitude or a size. There was no direction involved. So when we're going to calculate our distance, we are not going to take into consideration when the object is traveling in a different direction. We're still going to be seeing it as all traveling in one direction, because our distance do not have a direction. Now let's go and take a look at how we will be calculating our distance from a velocity time graph. If you can remember, if we've been given a velocity time graph and we would like to go and calculate displacement from that, now remember, distance will fall in the same category as displacement, with the only difference is that it doesn't have a direction. So calculating displacement or distance from velocity, we'll be using the area of the graph. So the areas that we would need to take into consideration is obviously all the areas underneath the line of the graph up till the x-axis. Now over here, we're going to break this area up into two parts. We're going to have a little triangle here at the top, and then we'll have a square at the bottom of it. So there's two areas that will make up this first part from A to B. When we take a look to B to C, we'll have this area of a rectangle over here. C to D, on the other hand, again, is going to be a triangle. D to E, we're going to be cutting our D, E, and F here in half, so that our D to E is also a triangle, and that we can see is my last part, E to F, also a triangle. So we're going to be having a triangle here at the top, plus a rectangle, another rectangle, triangle, triangle, triangle. So we're going to add up all of these areas, not taking into consideration the negatives, only using them as positive values. So we're going to be adding every single one of these values in. Taking again our little triangle at the top, remember it's half the base, which we'll see is 2, the height is between the 10 and the 15, which means it's 5, and then we're going to have the rectangle at the bottom, which is 10, which is that height times 2 of the base, and then we're going to have a rectangle BC, which is 1, 2, 3 times 15 to the top, plus half of the base of 5 to 6, which is 1, and the height is 15, plus, now not take into consideration the fact that it's negative, a half of base, which in this case is going to be 2 times 10, plus another half times 1 times 10. And that's going to end up giving you 92.5 meters. Now, should they have asked you rather to calculate the displacement instead of the distance, you would still use the area, with the only difference you would add in your negative values as they are given on the graph. Now, from your A up till D, all of the values was positive, but my DE triangle over here had a negative 10, so we'll put in the negative 10, and our EF also had a height of negative 10. Now, if we add that back into our equation, we'll find our displacement to be then 62,5 meters, because we had to subtract those areas going in the opposite direction. So for distance, you'll just add them up without any negative values, whereas with displacement, you'll add in your negative as in the graph, and then you'll see you'll end up with a different value. Now, because it's displacement and we end up with a positive value, it means that we are still traveling overall in an eastern direction.